Welcome back. In the last video we discussed cyclotomic extensions, which are extensions obtained by adding roots of unity or roots of 1. Okay, and the main theorem we proved in the last class is the following. If you have a positive integer n and f is a field satisfying star, remember star is the condition that characteristic of f does not divide n if the characteristic is positive or that characteristic is 0. Okay, so that is a standard assumption for Kummer and cyclotomic extensions. And then you take the splitting field of the polynomial x power n minus 1. That is to say that you have added the roots of unity, nth roots of unity to f. Then there is an injective group homomorphism from the Galois group to the multiplicative group of integers modulo n. And as part of this, we constructed a specific homomorphism by observing that if you take the Galois group, an element of the Galois group, and you take a primitive nth root of unity, when you apply sigma to zeta, you get zeta power a number that is co-prime to n. And then it's easy to see that that's a group homomorphism and it is 1, 1. And we ended the last class by saying that in general, this map is not surjective, it is only injective. In other words, it's not necessarily an isomorphism, as the example with f equal to r or f equal to c shows. And we also commented, this is important for us, that cyclotomic extensions are abelian. So this is an important point for us that will come up later. So it is abelian because it's a Galois extension. That is obvious because it's a splitting field of a separable polynomial, and it is abelian because its Galois group is isomorphic to a subgroup of Z mod nz star, which is to say it is an abelian group. Okay. So now today we will prove that the map phi is in fact an isomorphism when the base field is Q. The map phi of the above theorem is an isomorphism when f is Q. Remember, of course, Q satisfies the star hypothesis because its characteristic is 0. So you have K equals splitting field of x power n minus 1 living over Q. And what we do know is, if zeta is a primitive nth root of 1, let's say in C, so it's a complex number, then K is actually nothing but, because I already showed that in the previous video, we already showed that the roots of unity form a fixed nth roots of unity, form a cyclic subgroup of C star in our situation. So once you have a primitive one, which is a generator of that cyclic group, you have all of them. So this is something to keep in mind. So what are we going to do? We are going to do the following. So let's let the irreducible polynomial of the primitive nth root of unity be f. Let f be the irreducible polynomial of zeta over Q. Right? So this is so then we know that degree of f is the degree of the extension, right, by definition of the degree, but this is of course k colon q because k colon q is f. So basically what we will show is, we will show degree of f is phi n. So by the way, I should remember here that we are going to fix n, right? So fix an integer n. All this is after you fix a positive integer. If the degree is equal to the Euler-Toshen function, that is the degree of this extension, but this degree is the cardinality of the Galois group, which is a subgroup of Z mod nz star, but if they are equal, then it is an isomorphism. So I will explain this when we come to it. Okay, so the claim that I want to prove, which proves this statement for me, is the following. Let P be a prime number, so it's a prime integer that doesn't divide n. Then I claim zeta power p is a root of f. Note that f is not x power n minus 1. I mean that sometimes we use the notation f equal to x power n minus 1 maybe in the previous videos, but here we want f. In fact, we do know that f cannot be equal to x power n minus 1 because f is the irreducible polynomial of zeta. X power n minus 1 is not an irreducible polynomial of over q, so it cannot be that. So what I want to show is that zeta power p is a root of f. So why is this? Note that first we note that zeta is a root of x power n minus 1, of course, because it's a primitive nth root of unity. So this means x power n minus 1 equals f times h for some h in qx, right? Because f is the irreducible polynomial of zeta, x power n minus 1 is some polynomial which has zeta as a root, so f divides that in qx. But now I want to make the following remark, that in fact h of x is in zx. Okay, so because f and x power n minus 1 are integer polynomials, if f divides x power n minus 1 in qx, it divides x power n minus 1 in zx itself. So this is a consequence of Gauss lemma. Okay, so there are several versions of Gauss lemma, but one that I will quote here is content of, if f and g are two rational polynomials, content of f times g is content of f times content of g. So content is defined as, if it's an integer polynomial, it is the least, it's the greatest common divisor of all the coefficients. If it's a rational polynomial, you first clear the denominators by multiplying by an integer, you take the content of that and then divide by that common denominator. And then Gauss lemma can be stated like this. In our case, so content of, let's say this is 1, but that's also content of f. Because f is a irreducible polynomial, so it is in fact a monic polynomial. So this forces content of h to be 1, which forces in turn that h is in zx. So a rational polynomial is in the is defined over integers if and only if its content is 1. So this is a subtle point. This is a basic, a ring theory here. When you learned about UFTs in ring theory, you learn this. So I'm going to use that fact. So you have now, let's come back to this. So you have x power n minus 1 equal to f times h. So if zeta is an nth root of unity, implies zeta power n is an nth root of unity. So zeta power p I want to write, right? Because power of an nth root of unity is an nth root of unity. So that means, right? So zeta is a root of, zeta power p is a root of x power n, which is f times h. But this means f of zeta p is 0 or h of zeta p is 0. In the claim, we are claiming that f of zeta p is 0. Right? Suppose this happens, we are done. Right? So suppose this is not the case. So assume that. So we now assume h of, and we are going to do some calculations and arrive at a contradiction. So now if h is an integer polynomial, I can define a new integer polynomial like this. So this of course is also an integer polynomial. H is some given polynomial in integers with integer coefficients, and I define a new polynomial where I raise x to the pth power. So then h1 of zeta, which is by definition h of zeta power p, is 0, right? So that means zeta is a root of h1. But f is the irreducible polynomial of zeta. Since f is the irreducible polynomial, we have f divides h1. F divides h1. So we can write h1 equals f times g for some g in qx a priori, but as above. Because f and h1 are integer polynomials which are monic, because h1 is monic because h is, but as above, g is in fact in zx, right? So now let's see where we are. So we have h1x, which is by definition h of x power p. Now this is a crucial statement I want to make. So this is the note. See, this of course is by definition, and this is because if you go modulo z mod pz and you take h power p, so this is like an example here. If hx is, let's say, x square plus 2x plus 1, then h1 of x, which is x power h of x power p, which will be x power p square plus 2 times x power p plus 1. So h1 is nothing but x power 2p plus 2xp plus 1. But when you go modulo, these are all integer polynomials, so you can go modulo p, which is to say that you look at the images of this under this. What is hx power p? This is x square plus 2x plus 1 whole p, but this modulo, because all the mixed terms will have coefficients divisible by p, they will vanish in z mod pz. This is the kind of argument that we have seen multiple times. So I really should write 2x power p plus 1, but this modulo p of course, but this is x power 2p plus 2 power p is 2 again, because in z mod pz anything power p is itself. This is of course h1 of x, right? So this is mod p, only mod p. With otherwise of course h power p is not equal to h1, right? So generally is not equal to hx power p. On the nose it is not, only modulo p it is, because this is the crucial argument here. So that means, now what do we have? So let's see, hx power p is equal to h1x. So hx power p is congruent to h1x, which is congruent to fx times gx modulo p. Okay, so strictly speaking, we are taking the images of these things. All these equations, all these polynomials are living in zx. We can take its image, their images in z mod pz x, and then this is what happens. This is to say that hence fx and hx have a common factor in z mod pz(x), right? So basically what I am saying is that this equation here, if you replace these 3 horizontal bars with 2 horizontal bars and make it inequality, this holds in z mod pz(x). That is the meaning of mod p. Now this holds in z mod pz(x). Now f z mod pz(x) is a UFD. So take an irreducible factor of f. let's say Rx is an irreducible factor of fx, then Rx divides fx times gx, and hence Rx divides hx power p, but because Rx is an irreducible polynomial and it divides the product, it divides hx. Remember, this vertical bar is division symbol for me. So this is all I am saying. So Rx is a common factor of f and h. Now what we have is, now note that x power n minus 1 is equal to f times h in zx. This is something that we had originally written, right? X power n minus 1 is f times h in zx. Now go modulo p. In other words, take the images of this 3 polynomials in z mod p zx. Because the modulo p map is a homomorphism, what you have is the image of this, which is of course this, which I don't want to write x bar, I'll just write xn minus 1 is f bar h bar in z mod p z x, right? But now we have a problem. But as we argued above, f bar and h bar have a common factor. Right? So that is exactly the statement. F and h have a common factor in z mod p zx. That means their images have a common factor. But then that means their GCD is, so the degree of their GCD is strictly greater than 0. That means the GCD is a non-constant polynomial, right? And then when I discussed separability and we talked about multiple roots, we argued that if 2 polynomials have their GCD of positive degree in the base field, in an extension field they have a common root. So in an extension field of z mod p zx, which of course is fp, f and h have a common root. But this is a crucial point. But then x power n minus 1 has a multiple root. Because x power n minus 1 is f bar times h bar. So if let's say small a is a root of f bar as well as a root of h bar, that means x minus a. So if a in some extension field k, let's say, if a in k is a common root of f bar and h bar, then x minus a square divides x power n minus 1, right? Because x minus a divides f bar and it also divides h bar, so it appears twice in the factorization. So that means a is a multiple root. But that's a problem, because why is this a problem? X power n minus 1 has distinct roots. We are in characteristic 0 now, so I'll just say C. It has distinct roots, right? It has n distinct roots because there are n distinct nth roots of unity. So that this is not possible. That is to say that, so that's all, we are done with this claim. we proved this claim because we assume that zeta power p is not a root of f, and then h of zeta power p is 0, and that is where we went wrong. So after that our analysis shows that we get a contradiction, hence is a root of f. Now this is an immediate implication. Now we can show that if I and n are co-prime and I is less than n, then zeta power I is a root of f. Why is this? The reason for this is we write the prime factorization of I. Let's say I equal to P1 through PL. So, and since I and n are co-prime, this is the GCD is 1, implies P1 and PL do not divide n. But then this implies zeta power P1 is a root of f. Right? If zeta power P is a root of f, by the claim, this implies zeta power P1 power P2 is a root of f. Because if you go back to the proof, what we critically used is that zeta is a primitive nth root of unity. Okay, so if zeta is a primitive nth root of unity, zeta power P1 is a primitive nth root of unity. So its power, so zeta is a root of unity, which is a root of f. Then the claim shows that zeta power P is a root of f. So what we really show is that if any z is a root of f, z power n equal to 1 and z is a root of f, implies z power p is a root of f. That is exactly what we have shown, because zeta is a root of x power n minus, it is a root of x power n minus 1 because z power n is 1, and then it is a root of f. So then the proof will go through. So if zeta power p1 is a root, zeta power p1 power p2 is a root, which in turn implies zeta power p1 p2 is a root, so p3 is a root, and like this, and finally zeta power I is a root. Because I is a product of P1 through PL, we go one by one and conclude that zeta power I is a root, and hence zeta I is a root of f for all I in Z mod nz star. Right? Zeta power I is a root of f for every I less than n co-prime to n, which is means for every I in Z mod nz star, which is to say f has at least phi n roots, because Z mod nz star has phi n elements. So this is the Euler function. Everything in Z mod nz star is an integer less than n, it comes from an integer less than n, which is co-prime to n, and for every such I, f zeta power I is a root, and they are all distinct, of course. So f has at least phi n roots. This means phi n is less than or equal to degree f, which is equal to k colon q, which is equal to Galois k over f, and this is because k over q is Galois, right, and k is q zeta. Okay, but now this is less than phi n, and this is because by the previous theorem, which I recalled at the beginning of today's video. We exhibited an injective map last time between Galois k over q into Z mod nz star. So the order of this group is less than or equal to the order of this group, which is phi n. So now we are done. This means all these numbers are equal. So degree f is phi n. Okay. So this is to say that, which is also the order of the Galois group. So I should really put bar here, order of the Galois group. But that means this is a subgroup, but their orders are equal. So phi from Galois k over q to Z mod nz star this particular map is an isomorphism, right? Because this is an injective map between two groups whose orders are two finite groups whose orders are equal, so this must be an isomorphism. So that's all. So this shows that the Galois group of K over Q is Z mod nZ star. And as I remarked at the beginning, this is only true for base field Q. In general, this is not an isomorphism. For example, if you take K to be R or C. Okay. So as a corollary, what we know is that when P is prime, the cyclotomic extension over Q adjoined zeta pth root of unity has to have degree p minus 1, but let me remark that we already knew this. Because x power p minus 1, x power p minus 2 plus x plus 1 is an irreducible polynomial by Eisenstein criterion. And it is the irreducible polynomial of zeta p, right? Because zeta p satisfies this polynomial which factors like this, and this is irreducible. So in other words, when you take q zeta p over q, this is p minus 1, which of course agrees with phi of p. However, for non-primes, it required more work to prove this, because the corresponding polynomial is clearly not irreducible, and because n minus 1 is in general not the degree of the cyclotomic extension. So let me end this class by quickly discussing how to go about finding the irreducible polynomials of nth roots of unity where n is not prime. For n prime, this is that. For n not prime, we have to do the following work. So I'm going to define the following. So let d be a positive integer, then define phi d of x. So these are all going to be rational polynomials defined as follows. Phi d, it will be rational, we'll show. Phi dx is defined to be x minus zeta, product is over all primitive nth roots of unity. Okay, so a priori this is a polynomial with complex coefficients. Okay, before we proceed further, let me quickly give you an example. What is phi 1? So you take all primitive first roots of unity. So that is just x minus 1. What is phi 2? You take all primitive second roots of unity. There are two second roots of unity, 1 and minus 1, of which only minus 1 is the primitive second root of unity. So phi 2 is x plus 1. What is phi 3? Phi 3 is product of primitive third roots of unity. So there are two of them, omega and omega square. Remember, 1 is a third root of unity, but it's not primitive. So you have x times x minus omega times x minus omega square, and if you expand this out, you get 1, because omega plus omega square is 1. Okay, so my omega is omega. So because roots of, okay, this is something that I will write here, but you know this, because omega cubed minus 1 is 0. That means omega minus 1 times omega square plus omega plus 1 is 0, but omega is not 1, so this is 0. So this is exactly, this gives omega plus omega square is minus 1. That means that the roots, sum of the roots is minus 1, so the coefficient of x is minus of minus 1, and omega times omega square is 1. Okay, so this is okay. So this is the third cyclotomic polynomial. What is phi 4? You have to look at fourth roots of unity. They are 1, minus 1, I, minus I. But only these are primitive. Right? And these are not primitive. So you get x minus 1 times x plus 1. So the fourth cyclotomic polynomial is x square plus 1. And let me write one more example before we proceed. This actually happens to be just, okay. So these are called the cyclotomic polynomials. Phi dx is the dth cyclotomic. Okay, and as you see in these examples, they are all rational numbers. In fact, they are always they are rational polynomials, and in fact they are always rational polynomials. Okay, first I will remark that it is an easy remark. If you take x power n minus 1, this product is x minus zeta product over all nth roots of unity. You cannot simply take primitive nth roots of unity. Here roots of this polynomial are all nth roots of unity. So you take all nth roots of unity. But every nth root of unity is a primitive dth root of unity for some d dividing n. So the point is every nth root of unity is a primitive dth root of unity for some d that divides n. Right? Because you simply look at the least d. Right? That d is something between 1 and n. For zeta equal to 1, you get 1. For a primitive nth root of unity, you get d equal to n. And then zeta will be by definition a primitive dth root of unity. But because the order of the group consisting of all the zeta is, so this is a fact, so then d divides n. Okay, so I will leave this as an exercise for you, because if it's not a divisor, you can write n equals to dA plus b, and then you play around with these equations. Zeta power n is 1, zeta power d is 1, but then zeta power b will be 1, which will violate this statement. Okay, so the upshot of all this is that this can be written simply as, by grouping all the nth roots of unity into primitive first roots of unity, primitive all divisors of n, you group it into those primitive roots, you get simply the product phi dx. Phi d, remember, is only contribution to phi d is primitive roots. So you group every nth root of unity into the appropriate primitive dth root, and then you take the product and you get this. Okay, so now this is easy. So simple proposition, let me quickly do this proposition and we'll stop. So then we are making some statements here. Phi n x is a rational polynomial. Phi n x is irreducible. It is the irreducible polynomial of a primitive nth root of unity. I am working exclusively over Q now. So you take a primitive nth root of unity in complex numbers and you take its irreducible polynomial, that happens to be phi n, and of course the third statement is that degree of phi n is the Euler-Taussian function, which is exactly the consequence of 2. Okay, so let's prove this. Okay, so we know that, okay, so we know that let zeta be a primitive nth root of unity. So then certainly we know that phi n right? Because phi n is the product of x minus zeta for all primitive nth roots of unity. So x minus zeta will be one of the factors. So this is 0. Okay. So this implies moreover, what is the degree of phi n? This is the number of primitive nth roots. Again, just look at the definition of phi n. It is product over all primitive nth roots. So there will be as many factors as there are n primitive nth roots. So that is the degree, and that of course is phi n. So this gives, in fact this gives 3 first, right? So this, the degree is phi n. Now I claim that it is in Zx in fact. So let me correct this. It is in fact an integer polynomial. Okay. So why is that? So note that x power n minus 1 is product phi d dividing n. So let's play around with this. We know phi 1 is an integer polynomial because this is x minus 1. But what is x square minus 1? This is phi 1 times phi 2, right? This is in integer polynomial, monic integer polynomial. This is of course a monic integer polynomial. So by Gauss lemma, phi 2x is an integer polynomial. See, of course I already know that phi 2x is an integer polynomial, but I am trying to set up an inductive argument here. So phi 2 is an integer polynomial. Now let's do x cubed minus 1. So this is phi 1x, phi 3x, and as before Gauss lemma says that phi 3x is in integer polynomial. So in general, if you have x 10 minus 1, this is phi 1x, phi 2x, phi 5x, phi 10x, right? By induction, these are all in Zx, and hence this is in Zx, of course, and by Gauss lemma, phi 10 is in Zx. Okay, so you understand the general argument. So you write this. Okay, so you write this as product of phi d dividing n, but d strictly less than n, and then you have phi n separately. Okay, so this is in Zx by induction hypothesis, and this is of course in Zx on the face of it. So this means phi nx is in Zx. Okay, so that is the statement 1. But now 1 and 3 imply 2, right? So since phi n of zeta n is 0, degree phi n x is phi n, and phi n is in Zx, better imply that phi n is the irreducible polynomial of zeta n. Zeta n is an irreducible, maybe I should have just called that here. Zeta n is a primitive nth root of unity. Its degree is already phi n, we know, right? We already know degree of q zeta n colon q is phi n. So its irreducible polynomial will have degree phi n, but here is an irreducible polynomial. Here is a polynomial whose degree is the right number, right? Because that's the important, whose degree is right, and it has zeta n as a root, and it is an integer polynomial. All three together imply this. Okay, so this implies 2. So this proves a proposition. So this is a recursive method of constructing the irreducible polynomials of primitive nth roots of unity. So let me quickly do this example and then we will stop this class. So what is this example? So let me just go ahead and compute some other cyclotomic. So this is Phi1x, Phi2x, Phi3x, Phi4, Phi6x. This is not that, this is x power 6 minus 1. But this is x minus 1, this is x plus 1, this is x square plus x plus 1. Okay. So now you can go ahead and you can see that this Phi6. So basically you can also separately write this as x cubed minus 1 times x cubed plus 1. This can be further written as x minus 1 x plus 1. So I have this here times x square plus x plus 1 times x square minus x plus 1. Okay. So on the one hand, this is equal to this, because via this you can get this, and that's also equal to this. So now you can easily see that you cancel this, you cancel this, you cancel this. So the conclusion is Phi6x is x square minus x plus 1. This confirms also the fact that the Euler-Torsion number for 6 is 2. Okay. So you can factor this by familiar algebra rules and then use the recursive definition to cancel out relevant things, or you can directly divide. Okay, but it's more direct this way. So let me do two more examples. So x7 minus Phi7, of course there is not much to do, because for a prime number the cyclotomic polynomial is this. What about Phi8? For that, let's factor x power 8 minus 1. This is Phi1x, Phi2x, Phi4x, Phi8x. So this is equal to x minus 1, x plus 1, x square plus 1, Phi8x. So now of course you can multiply all these and then divide x power 8 minus 1 by that product to get this. Another way is you can factor this as x power 4 minus 1, x power 4 plus 1, which is x minus 1, x plus 1, x square plus 1 times x4 plus 1. Right. So this is equal to this. Okay. Now you can see that you can cancel these three factors. So the conclusion is Phi8 of x is x power 4 plus 1. And this of course confirms that Phi8 is 4, but also this you should recall from earlier we worked out the Galois theory of this extension before. The Galois group here is in fact Z mod 2 cross Z mod 2. Okay, so this is a good point to remark. If P is prime, is a cyclic extension, right? Because this is the Galois group is isomorphic to Z mod P Z star, which is a cyclic group for order P minus 1. But if n is not prime, Q zeta n over Q is not cyclic in general. As this example shows, right? Example n equal to 8. Here the order is 4 and the group is Z mod 2 cross Z mod 2. So it is not a cyclic group. However, it is always abelian. This I already argued. Any cyclotomic extension is abelian. Okay. So and the last thing I'll write is you do a similar kind of calculation to conclude that Phi9 is x power 6 plus x cubed plus 1. Okay. So check this as an exercise. Okay. So the last point is not quite required for us when we do solution by radicals, but I thought it's a nice way to learn how to compute the cyclotomic polynomials, which are the irreducible polynomials of primitive nth roots of unity. So in the last 1 or 2 videos, what we did was we learned about general cyclotomic extensions for any field f whose characteristic is 0 or it doesn't divide n. we learned how to compute the cyclotomic extension. We showed that it's an abelian extension. It's Galois and the Galois group is abelian by exhibiting an injection into Z mod NZ star. In general, that injection is not an isomorphism. However, for base field equal to Q, it is an isomorphism, and we proved that. And then we learned how to compute the cyclotomic extensions, how to compute the cyclotomic polynomials. Let me stop today here. In the next class, we will start learning about solving polynomials by radicals. Thank you.